Welcome to the first lesson in our unit on reactions and stoichiometry. This first video will cover learning goal 5.1a, representing chemical change, or what we call chemical equations, and more specifically it will also simply cover the success criteria A and B for that learning goal. The next video will cover the success criteria C and D for this learning goal. So looking at the learning goal and the success criteria that this lesson will cover, the learning goal, 5.1a, I understand how chemical reactions are represented. And our success criteria, two different success criterion. Criterion A, I can define and identify chemical reactions. And success criterion B, I can write chemical equations and explain their format. So jumping right in here. What is a chemical reaction? Well, a chemical change or a chemical reaction, and those two terms are identical. Okay? A chemical change is a chemical reaction, vice versa. It's a process where one or more substances produce one or more new substances. Now, we had just a few short demonstrations in class where I showed you some examples of chemical reactions, and what we focused on was how we could observe those and identify evidence that showed us a chemical reaction was taking place. And we'll get to that here in just a second. But whenever we say a new substance is formed, what happens is atoms are combined, separated, and or rearranged to form those new substances. So it's not as if this new substance just comes from nowhere. The new substance or substances that are produced come from the starting materials. The atoms are simply arranged differently, whether they're combined, separated, or rearranged, to give us those new substances. So just a schematic here to help us understand this. Two different reactions you see here, and these are just generic, where in this first one I have some compound which involves atom A and B in a compound, and then that is reacting with atom C, which is just by itself. And then notice how the atoms have been rearranged here, where B is now with C and A is now by itself. So A and B got separated and B and C got combined to give us our new substances. And on this second reaction here, we can see that A and B have been separated, as have C and D, and then A and C are now together and B and D are now together. And so we can see that the atoms are separated, they're combined, they're rearranged to give us these new substances. Speaking of this schematic here, notice the terms reactants and products. These will be two terms that we use a lot with understanding chemical reactions. Reactants, those are just the starting substances, or if you just have one, the starting substance. So in this first reaction, AB would be a reactant and C would be a reactant. In the second one, AB is a reactant and CD is a reactant. Because those are the starting materials, or the starting substances. The product, or products, that's what we call the new substances. So in the first reaction, A is a product, as is BC. And in the second reaction, AC is a product, as is BD. So the question now is, how can we identify that a chemical reaction has taken place? And this is what we focused on with those demonstrations in class. So chemical reactions, they give evidence of a new substance being produced. Sometimes it's obvious, sometimes it's pretty subtle. So we need to make sure we're familiar with some different ideas. One thing that can occur is that we see a color change as a result of a process. So for example, think about a banana. You go to the store, you buy a banana, it's nice and yellow, maybe even a little bit of green tint to it, and after a few days it looks like this. This color change is indicative of a chemical change, because whatever is now producing this brown color is something different than was there before. And so there's obviously something new there, so we have a chemical change. Along with that, if you think about a banana, if you were comparing a banana to when you first bought it at the grocery store to say a week or 6, 7, 8, 9 days later, there'd be an odor change, okay, if you were trying to smell it, and then there'd also be a taste change. This banana here would taste very different than the same banana 5 days ago before it was starting to have all those brown and black spots on it. Now in chemistry we often don't talk about taste changes because we often don't go about tasting chemicals because that can be a bit dangerous for our health. But when it comes to food, it's an obvious thing to look at. And all those pieces of evidence there are indicative of a chemical change or a chemical reaction occurring. Another one that's very common is the release or the absorption of energy. So for example, if light is given off, okay, light is a form of energy, as is heat. So when we talk about release or absorption of energy and releasing or absorbing heat, a lot of times what coincides with that then is temperature changes. So if we think about this process here, we can't exactly see what's happening here, but obviously there's a lot of light being given off. It appears as if there'd be a lot of heat being given off because something is burning, and so the temperature is going up. And so that temperature increasing is indicative of energy being released, and that is often a piece of evidence for chemical change or chemical reaction. Another one that's very common is the production of a new state. So what we're talking about here is not simply phase changes. We're not talking about boiling water to make your macaroni, or the chocolate the chocolate bar melting in your pocket because you forgot it was in there. Those are not chemical changes, because those still have the same substances that you started with. If you think about a chocolate bar melting in your pocket, it's still chocolate. Okay, it's still the same stuff that's there. Now it's just in the liquid phase. Same thing with boiling water. You still have water, it's just no longer a liquid. It's now in the gas phase. So that's not what we're talking about when we talk about production of a new state. We're talking about we have a reaction, and instantaneously, as a result of that reaction, we're starting to get a new physical state produced. So for example, take a look at this picture. Here we're mixing two solutions. I know it's kind of hard to see, but there's a clear solution here in this pipette, that glass tube you see there, and there's a clear solution down here in the flask. And we mix those two and we get this yellow substance. So there's a color change, but that substance you can see is a solid. Okay, I can see it starting to accumulate there. If it was a liquid, it would spread out throughout the entire flask there. I can see we all of a sudden get a solid produced. Okay, same thing here. This looks like some sort of milk product that is spoiled. You start to get the chunks in the milk. I would not recommend consuming that. If that is in fact the case, would not be very good for your health. Oh, here's another example. We see a gas being produced here. This is one that we saw in class with the demonstrations, the simple idea of mixing vinegar and baking soda. We get a gas produced, and again, that gas is not a result of a phase change where, for example, we boil water. Just we mix those two things, the baking soda, which is sodium bicarbonate, with the vinegar, which is simply a solution of acetic acid, and those two produce a gas. In this case, it happens to be carbon dioxide. Okay, so we can see here in this picture that a gas is being produced, a good indicator of a chemical change. So how do we represent these chemical changes or chemical reactions? Well, we represent them by writing chemical equations. So what a chemical equation is, it uses symbols and formulas to represent substances that are involved in a reaction. You will see me use this notation, RXN, quite often to use some shorthand for reaction, just so you guys know. The basic format for any chemical equation is as follows. We write the symbols and the formulas for any reactant or reactants on the left side. Then we separate them from our products with an arrow that always goes pointed from reactants to products, and the symbols and formulas of our products go on the right side. So here are some examples of what we mean by that. So in this one here, we have water. I can see that because it's H2O and it's in the liquid state because the letter L there is in parentheses, and we're forming hydrogen and we're forming oxygen. So if we were to write this reaction in a sentence, we might write something like liquid water produces hydrogen gas and oxygen gas. Now do note it is H2 and O2 because those two are diatomic. So you will want to go back and review which elements are diatomic. Recall there are 7 of them. Hydrogen and oxygen both happen to be diatomic. And notice we're putting the physical states for those substances in parentheses. L for a liquid, G for a gas. Here we have a different reaction. So notice we have, in this case, we have 2 reactants. We have reactant 1, reactant 2 here. In the first example, we just had the 1. Notice this too as well, that we separate substances with plus signs. So in the first example, we had 2 different products. We separate them with a plus sign. In this second example, we have 2 reactants. We separate their formulas with a plus sign. Same thing on the products. We separate the formulas with a plus sign. If we were to write out this particular reaction in a sentence, it might be something like this. Solutions of silver nitrate and sodium chloride. So solutions, this symbol here, AQ, stands for aqueous, and we'll talk more about that on the next slide. But it just means it's dissolved in water, so it's a solution. So solutions of silver nitrate and sodium chloride yield. That's another word that we can use instead of saying produces. It's the same thing though. It doesn't mean anything different. Yield solid silver chloride. So notice our silver chloride is a solid, so S is in parentheses, and aqueous sodium nitrate. So again, aqueous meaning dissolved in water. We use AQ there for that symbol. So when we talk about a chemical reaction, our reactants, they yield, they produce, they form our products. So anytime you see this, produces, yields, forms, that's where your arrow is going to go to represent that. So here are some common symbols that we will see in writing chemical equations. The arrow we just talked about, meaning yields, produces, forms, that's what separates your reactants from your products. A plus sign, that is used to separate substances on the same side of the equation. So if you have more than one reactant and or one product, you separate each symbol or each formula with a plus sign. And then some symbols that we use to represent physical states: S for solid, L for liquid, G for gas, and then AQ to mean aqueous. That just means dissolved in water. Notice the same root of the word aqua is in that word aqueous. That's where it comes from. It means dissolved in water, so it's a solution. And then something else you might see from time to time, although it's not as common in this class, if you see the triangle, a triangle symbol, that means we're talking about heat, whether we are heating up the mixture to get it to react or heat is produced. We'll see that from time to time. So just one more example here, and kind of going backwards here I give you the sentence. When solid sodium is placed in water, aqueous sodium hydroxide and hydrogen gas are produced. So the first thing we want to do is think about what our reactants are. Well, here our reactants are the solid sodium and the water. And so notice that goes on the left side of the equation. We have sodium, the symbol for that's Na, it's solid. So we have the S in parentheses. And then we have water, which is H2O. Now we're not told specifically that it's liquid water, but it's a pretty good approximation to make. It's a good assumption that it's probably a liquid, so we put an L there. And then we're told we have aqueous sodium hydroxide, that's NaOH, aqueous, and hydrogen gas are produced. And you can see that hydrogen again is diatomic, so H2, and those are our products, so they're on the right side of the equation. So let's just look at some more examples of writing chemical equations. So in these here, I'll give you a statement just like I did on that last example, and we'll show you how the equations are written. So the first one here, solid copper reacts with a solution of silver nitrate to form solid silver and a solution of copper 2 nitrate. So we want to identify what are our reactants, what are our products. Well, copper is reacting with silver nitrate, so those are our reactants. So copper solid, so Cu with the S in parentheses, show it's a solid, plus, because again, we separate reactants with plus signs, solution of silver nitrate. Well, the formula for silver nitrate is AgNO3. It's a solution, unless we're told differently, and for our case, this will rarely happen, but unless we're told differently, it's dissolved in water. So that's the aqueous, AQ. Now these two form, so we use an arrow. We don't write an equal sign. It's not a math equation. We use an arrow to show that they are forming or producing something new. Solid silver, so that's Ag with the S in parentheses to show solid, and a solution of copper 2 nitrate. The formula for copper 2 nitrate, CuNO3 and it's a solution, so it's dissolved in water, so AQ. One thing you might be noticing here is you will want to go back and review your nomenclature rules, how we go about writing formulas to help you with writing these equations. Let's look at another example. Carbon dioxide gas and water vapor are formed when liquid propane burns in air. And a hint I give you here is, what is something reacting with when it burns? Well, notice here, carbon dioxide gas and water vapor, they are forms. Those are your products. Your reactants here are liquid propane and whatever it's burning in air with. Well, when something burns in air, it means it's reacting with oxygen. So here our reactants are the propane, and I just realized this. I forgot to put the formula for propane in the problem here. I was going to do that for you. I would not expect that you would know what the formula for propane is. That's C3H8, and we're told it's a liquid, and it's reacting with oxygen. So O2. Whenever something burns in air, it means it's reacting with oxygen. So those are our reactants. And then we are forming carbon dioxide gas, so CO2 gas, and water vapor. Now, water vapor telling us it's in the gas state, so H2O gas that you see there. Here are some tips to remember whenever writing these equations. Are your reactants and products on the correct side? So think of the last example. If you had just written your equation in the exact same order that the sentence was read, you would have had your reactants and products on the wrong side of the equation. Reactants are the starting materials, products are the new substances, what's getting formed. Substances, they get separated with plus signs between substances on one side of an equation. Chemical equations, they do not contain equal signs. Do not contain equal signs. Make sure that you review your nomenclature and formula writing to make sure those are right. And don't forget the diatomic elements. Remember, there are 7 of them. If you need to ask which ones those are again, please do. So here are a couple of practice problems. I will just put the sentence up here. Pause the video, try it yourself, see if you have done it correctly. So write chemical equations for each reaction. So here's the first one. And just go ahead and read that, pause the video, try it yourself. All right, so here is the answer to this one. Just clicking through here. So notice potassium metal is placed in water. The fact that it's a metal, it's going to make it a solid. Placed in water, so it's a liquid. We get hydrogen gas and aqueous potassium hydroxide formed. So that's the H2 gas and the KOH aqueous AQ. Here's the second one. So again, this one, make sure you get your reactants and products on the correct side. Here our reactants are iron, metal, and oxygen. So Fe plus O2, and then the solid iron 3 oxide is our product. So Fe2O3 solid is our product. And lastly, here's a final look at our learning goal and success criteria.